Good afternoon, I'm Mr. Rich. Thank you for joining me. Let's put what we've learned recently into practice. Inflection point and concavities. We have this function f of x is equal to x minus x cubed. We have to find the relevant concavities or any relevant local maxima, minima, and the inflection point. Start very quickly here with this first order derivative, and you have 1 minus 3x squared. Consider the fact that an interval is not given, so you don't have to worry about absolute or global extrema. You also have the second order derivative you can do right here, minus 6x. Everything is well into place over here. You know, when you're looking right here at your original function, you know based on x being a 0, you'll have an output of a 0. It'll go to the origin, so that gives you a good point over there for your graph. When you're looking right over here, take this first order derivative and let's see what type of critical points develop. Make it equal to 0. 1 minus 3x squared is equal to 0. Minus 3x squared is equal to minus 1. 3x squared is equal to 1, and then x is equal to plus and minus 1 over root 3. Those are the x-axis values for two potential critical points that we are seeing. We can get their y values too. We'll have a minus 1 over root 3, and then you'll have a positive 1 over root 3, and we can determine the y value very much from right over here. I'm getting here a 0.3849 plus or minus, and you get a 0.3849 minus here, and you get a positive 0.3849 over there. It's a difficult number to here present in terms of a fraction, but we can do that. We can convert everything here with regards to that fraction x-axis value even into a decimal. In the end, what we see is we have a minus 0.577 comma minus 0.3849, and then we have a positive 0.577 comma 0.3849. These represent perhaps a relative maximum, a relative minimum. Which is which? Put everything right in here. When you put this x-axis value here, this one right over here, you get a positive outcome, and that tells you you're looking here at a relative or a local minimum, because when you put this x-axis value here, it generates a positive in terms of your second order. When you put this over here, it retains a negative, and you're looking here at a relative or a local maximum. If you were to graph it out, and let's graph it out because we have some points available. We have a graph 0 comma 0, we have a minus 0.5. we don't have to be too accurate here. It'll be a point over here, and then positive 0.577 and 0.3849 will be a point over here. Very likely your graph is going to come like this and go like this. If you were to look at the first order derivative test, looking at everything over here, if you were to draw tangent lines, they would be pointing downwards here. You'd see minus, minus, minus. Here you'd see a 0. Here it would become a positive. Remember, I'm only talking about the first order derivative test here with regards to the signs. You're seeing a switch here from a minus to a positive, and that tells you you're looking at a local minimum. Then you're seeing a switch here from a positive to minus, that tells you you're looking at a local maximum. So indeed we're right. This right here is my local maximum, and here's my local minimum. Now I'm just going to remove these signs out of the way because I don't need them anymore. Now we'll focus again on the second order derivative, because we now need to determine the inflection point. The inflection point can very well be determined just from looking at this. If you do minus 6x and you equal it to 0, you'll get x is equal to 0, and that will give you right here that you have a 0 comma 0 in terms of your inflection point. Your IP is 0 comma 0. And another way you can do the exact same determination is you'd have to plug in values. Your inflection point would be located somewhere between here and here, between this lowest point and this highest point, between a concavity up and a concavity down, because here the local minimum represents a concavity up. The local maximum here represents a concavity down. Where the second order derivative changes sign is where you see this inflection point form, and where you see the concavity up convert to concavity down, you see an inflection point develop. I'm seeing an inflection point right here at 0 comma 0. You could have also picked these values here slowly and plug them in into your second order derivative. Any value between this minus 0.577 to 0.577, you put values on either side of this origin and see where the positives became the negatives, and you would see that. But the inflection point here would very well be 0, 0. A good tip is for your inflection point determination, just make this equal to 0, and it would very well help you out. Minus 6x equals 0, x is equal to 0. If x is equal to 0, then putting everything here gives you your y equals 0. So inflection point is determined, and we'll put that right over here. Inflection point 0 comma 0. Now let's, at the very last part, represent the intervals of concavity up and concavity down. Your concavity up interval is coming all the way from minus infinity and is coming up to this x-axis value of your inflection point to 0. Not including 0, but up to that. Your concavity down is going from that x-axis value of your inflection point and then going all the way up to positive infinity, and there it is. Everything has been presented. We have our critical points, which were a little weird in presentation because they're difficult numbers in terms of fractions. Minus 0.577, comma, 0.3849 negative, and then positive for both. Relative minimum, relative maximum, relative minimum, relative maximum, inflection point 0, 0, my concave up interval, and my concave down. Remember here, for concave up, any tangent lines will be located below the function. For this concave down, any tangent lines will be located above the function. That right there would very well remind us of what we were learning in that original video when we started looking at inflection points from a comprehensive perspective. But that's it for this video. Thank you for watching. Stay tuned. Have a nice day.